Good morning. Well, whatever it is for you. Hope you're doing okay, staying safe and sound and healthy. I'm following up now with what I covered in the last lecture. That one is entitled March 22nd, 2020. I'm going to do better with the titling of this one. But in that last little 16-minute lecture, I covered the definition of static equilibrium and talked about Hooke's law. So here we're going to do a problem involving static equilibrium out of the back of chapter 8. And I've got it drawn up on the board there already to save a little bit of time. So the problem goes like this. You've got a beam, which is like a long rod or something like that, that is being supported by a wire with tension on it up against a wall. And so here's the beam. It's 1 meter long. It's got a mass of 1 kilogram. It's attached by a hinge that's free to rotate on a wall at this point. It's horizontal, and the opposite end of it, opposite of the wall, is being supported by a wire that is attached further up the wall at a 30-degree angle to the horizontal. So the question in the problem was, what is the tension on the wire? We've got to solve for the tension on the wire. I'm going to go at 1 or 2 better, and we're going to solve for the force acting on the opposite end of the beam where it's up against the wall due to the hinge. And we're going to find the x component of the force due to the hinge and the y component of the force due to the hinge. So this is a very standard kind of first problem in static equilibrium that's in 2 dimensions. The example that I gave you in the last video was a 1-dimensional problem. Remember, the forces on the bridge were either acting up or down, and that was it, so only 1-dimensional. This is 2-dimensional. So now, instead of just summing the forces once, we have to do it twice for both dimensions, the x and the y. So I'll show you how that goes. First thing to do, just like with any problem involving forces, draw the forces in that are acting on the system. So I'm going to go ahead and do that. You've got the weight acting at the center of the beam, at its center of mass, acting directly downward. Okay? And that weight is m times g. Okay? And I'm just going to call that, since this is 1 kilogram, 1 kilogram times g, and I'm going to call g 10 meters per second squared. That's going to give you 10 newtons of weight. Okay, so that's the weight. Now, the other forces that are acting, the tension in the line is definitely doing something to the rod, right, or the beam. Otherwise, it would rotate downward clockwise and be up against the side of the building, right? So there's a tension here along the direction of the wire itself attached to the far end of the beam, the right-hand end of the beam. Okay, now, like I said, we're also going to solve for the forces due to the hinge acting on the beam, okay? And we're going to worry about the horizontal and the vertical components. So let's just immediately break this single hinge force up into a part going in the horizontal direction. We'll call that Fx. And then there's also going to be a component keeping the left-hand end of the beam from sliding down the wall. There must be an upward force to hold it in place. So this is Fy. Okay, so there we have all of the forces acting on the beam. It's not accelerating. We don't have to provide an acceleration vector like we have in previous problems involving forces, but we do need to include one more thing, and that has to do with the fact that we have to choose a rotation point. The smartest thing to do with this particular problem is to choose the rotation point right where 2 of the forces are acting simultaneously, drawn in this image. That's right here at the hinge. I mean, if it's going to rotate, it's going to rotate about the hinge anyway, right? Okay, so my curly arrow goes there so that I can define my radial vector that's, part of the definition of torque. Okay, so here that's all you can do graphically. That's all you can do as far as artwork goes. But you need all that information there in order to do the rest of it. So now we're going to deal with the math part. So now the first criteria is that the sum of the forces needs to be equal to 0. Now here we're going to break it up into an x component and a y component. So now in the x direction, the horizontal direction, what forces are acting? Well, there's the hinge force here. So now I'm going to call this capital HX for hinge. Okay, not to be confused with the forces in the x or the y. So we've got the horizontal hinge force acting entirely in the positive x direction. And then we have to subtract from that the component of the tension that's pointing to the left. And that would be the magnitude of the tension times the cosine of 30 degrees. And that's got to be equal to 0 because it's not accelerating to the right or the left, right? So there we have a single equation, but we've got two unknowns. We don't know the x component of the hinge force. We don't know the tension yet. We want to find both of those things. So we're not done yet. We need another equation with those same two unknowns. So I'm going to sum the forces in the y direction now. Now in the y direction, let's see, acting upward we have the hinge force oriented in the y direction plus the tension times the sine of the angle, 30 degrees. Okay, so now that'll be the component of the tension that's oriented upward. And then the only downward force we have is the weight itself, so we need a negative sign there, right? So minus mg, and that should be equal to 0 as well. Okay, now here we have two equations now, but now we have three unknowns, hx, hy, and t. Those are all things we want to solve for, but we can't do it with only two equations if we've got three unknowns. We need a third equation, and we get that by summing the torques now. Remember, that's the other criteria that needs to be met when you're doing a static equilibrium problem. So let's see, we chose our rotation point to be right at the hinge, so that means hy and hx cannot exert a torque, right? Because torque is equal to the magnitude of the force times the magnitude of the distance that the force acts from the center of rotation times the sine of the angle between these two vectors, the radial vector and the force vector. Well, r is going to be equal to 0 because the distance of hx and hy from the center of rotation, the way I defined it, is 0. So anything times 0 is 0. So those don't exert any torque. Now, the weight of the hinge is trying to make the whole beam rotate in the clockwise sense about the hinge, right? So the weight of the beam is 10 newtons, and it's acting half of the length out from the center of rotation, so half of a meter. So the torque due to the hinge will be the magnitude of the weight of the torque due to the weight of the beam will be the magnitude of the weight of the beam times the distance that it's acting out from the center of rotation, 1/2 meter, times the sine of the angle between the force vector and the radial vector that points along the beam. So that's, horizontally. So the angle there would be 90, and the sine of 90 is just 1. So I'm not going to bother putting sine 90 here. Now we have to subtract from that the torque due to the tension on the support wire out here on the end of the beam, which is trying to make the whole thing rotate in the counterclockwise sense. So now that is an unknown tension, T, so we just have to use a symbol for it. We do know its distance, though. It's 1 meter, the total length of the beam. And then it's acting at an angle of 30 degrees to the radial vector, right? so we need to include the sine factor in the torque due to the tension on the wire. So, right, because the radial vector points along from the center of rotation out to where the force is applied all along the beam, and the torque itself is 30 degrees off of that, so we need to include a 30 degree, sine 30 degree there. Negative sign because counterclockwise torque due to the tension in the wire. Positive term here because clockwise torque due to the weight of the beam. And that should be equal to 0. Okay, so, well, guess what? We've got enough information in that third equation to solve for the tension right away. And if we solve for the tension, then we can use that plugged into one of the top two equations to solve for the other two unknowns, the hinge force in the y and the hinge force in the x. So let's go ahead and do this. I'm going to add this term to both sides. It'll come over here, become positive, then divide by 1 meter sine 30, and that'll isolate the tension. The tension here should be equal to 10 newtons times 1/2 meter. That would be 5 Newton meters, and then I'm dividing that by 1 meter sine 30 degrees. Okay, there I've isolated the tension. Notice the meters will cancel. You'll be left with units of newtons. That's good because that's tension and it's measured in units of newtons. Sine 30 is 1/2. 5 divided by 1/2 is 10. So the tension is 10 newtons. By the way, if you had used G is equal to 9.8 meters per second squared and this instead of 10 meters per second squared, this value would have been 9.8 newtons. So we're only off by 2%, but it just makes for ease in the calculation. So, hey, we found what they asked for, but I decided that we should take it just a little bit further and solve for these two other variables. So here I'm going to solve first for the hinge force in the x direction, and I can do that by adding t cos 30 to both sides of the equation that isolates hx. So hx, the hinge force in the x direction, will be equal to t cos 30, and t is 10 newtons times the cos of 30 degrees, and that gives me 8.66 newtons. Okay, so there I found the horizontal component of the hinge force. Now the vertical component of the hinge force, hy, let's see, let's add mg to both sides, subtract t sine 30 from both sides, and that'll isolate the y component of the hinge force as being equal to 10 newtons, that's tension, times the sine of 30 degrees, and then, we need to subtract that, right? And then add to that mg, and mg is 10 newtons. Okay, so let's see, sine 30 is 1/2, so this is going to be 10 times 1/2, or 5, so it's minus 5 plus 10, so that's 5 newtons. Okay, so there we've solved for all three unknowns. Yeah, that's the extent of the problem. That's a two-dimensional static equilibrium problem. Here we basically had three criteria that need to be met, right? Instead of just summing the forces one time, we have to do it twice in the x and the y. So the sum of the forces in the x is 0, sum of the forces in the y is 0, and the sum of the torques is 0. And taking all of that into account, we were able to solve for the three unknowns here. So we took that problem number 13 a step or two further. If anybody has any questions, please call me at 407-222-0803. That's my cell phone, and you can do that basically anytime, except real late. I go to bed pretty early, but I get up pretty early too, so you can call pretty early. Pretty much anytime. Okay, so I'm going to go ahead and erase this and then do a problem involving springs. Okay, the problem involving springs that I wanted to do was on the same page, and it's problem 22. So 22, same page, 267. And that problem goes like this. The four wheels of a car are connected to the car's body by spring assemblies that let the wheels move up and down over bumps and dips in the road. When a 68 kilogram, about 150 pound person sits on the left front fender of a small car, the corner of the car dips by about 1.2 centimeters, about 1/2 inch. If we treat the spring assembly as a single spring, what is the approximate spring constant? Let's see. Excuse me. So here we have, say, the mass of the car and a spring and a wheel. Okay, now this spring has a spring constant K. Now here I'm assuming that we can think of, like they said, think of it as just a single spring. So if somebody sits on the car, they're applying an additional mass, M on top, and that's causing the spring to compress by a certain amount, delta X. Okay, the amount that it compresses, they said, was 1.2 centimeters. So that's 1.2 times 10 to the negative 2 meters, where M is 68 kilograms. Okay, I don't have my calculator with me, so I'm going to assume that G is equal to 10 meters per second squared. And that means that the additional force, little m times G, is going to be 680 newtons. Okay, so you exert an additional 680 newtons, and that causes the spring to compress a further 1.2 times 10 to the minus 2 meters. So knowing that, we can use the spring force equation, which, remember, is the spring force, or the force exerted by a spring on an object, is equal to negative K, which is its spring constant, times the amount of compression caused by that force. So hey, we've already determined the amount of we already know the amount of compression due to that force, and we know the additional amount of force, right? Okay, so we've got a force exerted downward on the spring, compressing it downward due to the person's weight, and it's causing this amount of compression. So you can solve for the spring constant here. The spring constant will be equal to that force of 680 newtons divided by the amount of compression it causes, 1.2 times 10 to the negative 2 meters. Okay, if you divide by 10 to the negative 2, same thing as multiplying by 10 to the positive 2. So 680 times 100 would be 68,000 newtons per meter, but we still have the 1.2 to worry about. Okay, 1.2 is 6/5, so let's see, if you multiply that by 5, you get 340,000. 340,000 divided by 6. So this equals 340,000 newtons per meter. And you divide that by 6. If you divide by 3, you get 113.3 thousand. If you divide that again by 2, you get 56,700 newtons per meter. This is rounded, but this should be the value of the spring constant of just a single spring that's behaving in the same way that those 4 springs are in the problem. Let's see. Okay, so that's the problem. And that was a problem strictly requiring the use of Hooke's law, which is what section 8.3 was about. So there I've given 2 example problems that incorporate the concepts that I talked about in the previous video. If you have any questions about any of this, please call 407-222-0803. You can text me, you can call me, please stay in touch with me. And hang in there, we're going to get through this, and stay healthy. I'll be back with more videos, and I might even make videos if you have specific problems, go through this chapter. If you have any specific problems that you'd like help with, if it's a good problem, I might do it for the whole class and put it on video. If not, I can just, if I don't have the time or that kind of thing, I could just do it for you, maybe on a sheet of paper, take a picture of it and text it to you. So we'll deal with this one way or the other. Y'all take care, please be safe, and it'd be nice to say that I could see you again this semester, but maybe by Skype. Y'all take care, bye.